Welcome to our workshop today on anonymizing financial data with fine-tuned SLMs and synthetic data. Next slide, please. My name is Alex Watson. I'm a co-founder here at Gretel and Chief Product Officer. And I'd also like to introduce Dr. Ali Arsanjani, who is the Director of AI ML Partner Engineering at Google, and Dr. Martin Van Segbroek, who is the Head of Applied Science at Gretel. We're going to start with an introduction that Ali is going to walk us through for patterns that they are seeing within Google Cloud of how customers are building successful generative AI applications inside Google Cloud. From there, we'll go into a quick overview of synthetic data, and then attack that really difficult problem of how do you customize an AI-based solution. In this case, we're going to be showing how to generate synthetic data that we can use to anonymize financial specific formats of text with really high confidence and a level of customizability. So exciting stuff. Let's go ahead and jump into the next slide, and I'll hand it over to Ali to give us a walkthrough of the generative AI lifecycle.
Wonderful. Thank you so much, Alex. So greetings, everyone. We're seeing an increasing level of sophistication of solutions that are happening. In the first instance, if we click once, please. We see folks selecting a model, prompting it, and then expecting the generative model to produce a result. As the needs start getting more sophisticated and you have things that the large language model was not trained on, we go to level 2, where we basically then retrieve information. And this is often done through a retrieval augmented generation, where we're accessing secondary information, augmenting the prompt, and then serving the model. Sometimes we have to go to a level 3 of maturity in order to tune the data. This can be anywhere from parameter efficient fine tuning to full fine tuning. So there's a wide spectrum there. You can use retrieval augmentation combined with tuning your data on very specific domain specific, industry specific kind of areas, so that your model will be tuned to the jargon, the taxonomies, the ontologies of that domain. Even more sophisticated than that, on the next level of maturity, you will essentially look at the outputs that's generated from the large language model, and you can utilize the capabilities that we provide on the Google platform to ground the information, search for the information, evaluate the result that the large language model has produced. This gives an added level of security and guardrails, because you're now checking it against factual information that you actually can search for. At level 5, we're beginning to introduce a level of high-level orchestration between the LLMs using one major large model, and introducing primarily ML ops plus the generative AI space, which we often term as LLM ops. And lastly, we have at level 6, we have an increased sophistication in terms of the multi-agent systems that we're working with. We have increased sophistication in all areas, but also including how we prompt the model, how we tune the model, how we serve the model, and how we orchestrate between multiple agents, and how we conduct LLM ops. However, all of this is really only possible if you could click again, please, we have a level 0 of procured data that is prepared and curated correctly. In many cases, we don't have the option of obtaining that data directly for privacy concerns, et cetera, that Alex and our other colleagues will be talking about. So the need for synthetic data generation is paramount. And that is something that we'll be talking to you today. On to the next one. Again, the importance of preparing your data in this generative AI lifecycle. You can enter it in at multiple points. It's no longer kind of the, let's just get the data, train the model, tune it, and serve it, which is more of a linear model. We can attack the problem from any angle. You can start by definitely preparing the data, choosing a model, but at the core and central point of the new Gen AI lifecycle, you have evaluation, optimization, and observability, So you're constantly trying to evaluate the results of each of the components that you have in your architecture. Going on to the next slide, the architecture, if you can think of it as a reference architecture that supports all of these capabilities, for example, that you would have on the Google Cloud Platform, starting with enterprise search, enterprise building conversational agents, the prompting, the RAG, the serving, adapting the models, grounding your information, integrating with enterprise systems, governing the output of your models, orchestrating them in pipelines while monitoring the results. All of that is based on a foundation of running your compute environment on our hyperscale computing environment of TPUs and GPUs, all with the security, privacy, and responsible AI built in, so you get safe, vetted, grounded output. Now, critical to this process is the preparation of data. And critical to success in a given domain is tuning models for that domain with domain-specific data. So I'll hand it off to Alex to take it away from here.
Thanks, Ali. We're going to start with a really brief introduction to synthetic data. And really from the reason that if you ask 5 people what is synthetic data, you'll probably hear today still 3 different answers. With Gretel, we consider synthetic data, data that is created by a deep learning generative model. So under the hood at Gretel, we heavily use transformers. So we have pre-trained models that are trained across a variety of industry verticals to be an expert at the task that you're using it for. So the big use cases we see for synthetic data, I'd say there's 2 core use cases. One, you are bottlenecked around privacy concerns. You have data you want to work with, you want to share it, you want to collaborate on it, you want to train a generative AI model using that data, or fine tune it or make it available for RAG, and you can't because of privacy concerns with the data. The promise of synthetic data here is we can train a model to learn the distributions and the insights of that data to create an artificial data set that can be used in place of the real world data. And none of the data in this artificial data set can be pointed back to a single individual that the data was based on. So it gives you up to mathematical privacy guarantees, which really helps to enable data sharing, for example, in the financial space. Second use case is when you have limited data or no data at all, and you just need to make it better. And that's what we're going to dive into today. We're going to use Gretel's Navigator, which leverages a pre-trained LLM, and we're going to use it to create data when we don't have any. We have very limited examples that we can use to train a model to get really good at anonymizing data inside of financial documents. Next slide. Let's start talking about the pain point here. And I love this slide. This came from the Kaggle annual data science survey, and asking 16,000 developers, what is the biggest pain point that you see working with on data science or AI projects? And here you can see on the left, even just this data gathering phase, but also through the whole ML life cycle, you see this constant need to curate and collect and build and explore data. And you see 25% of an average project minimum up to 35 or 45% of a project just being spent working, curating the data. So the promise of synthetic data is that rather than requiring on data collection to help you augment areas where you might need more data, or human labelers, or even like human-assisted labeling, we can dramatically shorten that process and allow really fast experimentation and iteration. So later in the slides today, we're going to walk through actually a very practical example on some of the improvements we've seen at Gretel in our own fine-tuning experiments using synthetic data, and then we'll dive into a real life example for our use case around anonymizing financial data. Next slide. So we're going to be going through anonymizing financial documents, which can be tens, hundreds, thousands of different data types. While we are focusing on the finance vertical here and financial data types, I think the important part here is this can be very easily mapped to a variety of different industries, from healthcare, for example, to e-commerce. What makes this hard, right? It feels like anonymizing data should be a pretty solved problem right now. And unfortunately, it's not. It turns out that finding things that are sensitive, whether it's PII or customer ID or some sort of unique data format that you might have or something you care about, is very specific and can change quite a bit for each organization or company. So here we see, we have a snowflake here, but everybody's data is different. That is absolutely true. one NER model that's trained to recognize names may not work well in your data. So in today's experiment, we're going to synthesize data and we're going to experiment with a variety of different formats and really see where it's working well and where we can iteratively improve it using synthetic data. Traditional approaches like NER, we've been big fans of, we've used them for years. However, you hit some real limitations. So named entity recognition is a class of models, traditionally very early precursors to the language models that we'll be using today. While they can work well in very specific scenarios, they do not generalize well to data they haven't seen. And if anything changes about your data, whether it's the schema or the types of data you want to connect, you have to go all the way back to the beginning of the process. So LLMs, which I think we're all very familiar with, offer a lot of really promising benefits for this use case of identifying and anonymizing financial data. And why is that? You can prompt tune them. So if you have small customizations that you want to make to your model, you can simply just add to the prompt. Here's the new data type. Here's a few examples. I would like to go ahead and anonymize this as well. So it allows for fast experimentation. There are some downsides though. Compute requirements can be high. Historically, they are expensive to run at scale. So today we're going to walk through the use of, next slide, please. We're going to walk through the use of small language models, which is the same technology as an LLM. And as Ali Arsanjani has called that a few times, it is definitely a moving target. What is the difference between a small language model and a large language model? We commonly refer to anything in single-digit billions of parameters now as being a small language model. And today we're going to demonstrate the ability to fine-tune Google's brand new Gemma 2 billion and 7 billion parameter models. But here you can see you start to get this efficiency at scale and efficiency of processing with the flexibility of an LLM. So it's very promising. Next slide. All we need is training data. So we need to customize this. And the reason we need to customize it is you very quickly hit the limitations of in-context learning or prompt tuning. So for a quick introduction to that, anybody that is used to ChatGPT or Bard knows exactly what prompt tuning is. You're giving the LLM a set of instructions. If we're trying to tell it to anonymize 20 or 50 or 100 different data types, that prompt is going to get very complicated very quickly. And LLMs often, as the prompt gets longer and longer, start to not really realize which areas are important. So what we're going to do is we're going to collect a set of data that we can use to fine tune it and have it become an expert at data anonymization or data labeling, so that the prompt can be used just to fine tune the data. And here we're going to go through some of the problems that you have when it comes to data collection. First, you're working in a finance space, you're working with regulatory control data. Where do you get that data set to use to initially train your model to anonymize data? That's the same private data that you're trying to anonymize in the first place. So it's very sensitive. Might be hard to enable access to your teams. Another kind of logical thing is, hey, I'm just going to scrape the web and pull back data. And I'm sure we've all tried this before. It ends up being very low quality. Getting your crawler to work the way you expect is also hard. So it just doesn't work there. Collecting and labeling data for anybody in the data science world is the ultimate time sink. It takes forever and can delay your entire project and leave you right back in the problem that you started. And what that all turns into is weeks or months of data prep. And that is the promise of synthetic data and what we're going to try to show an alternative way to do today. Next slide. So synthetic data. What are we going to do? So we're going to leverage a model that is trained on a variety of different financial data types, financial documents, specific formats, things like that. We're going to ask it, so we'll use Gretel's Navigator model today. We're going to ask it to generate hundreds or thousands of different document types. We're going to ask it to mix in different types of PII that we want to detect, which we can also give it a description of what we're looking for. And the great thing here is that this isn't just a one-time data collection thing like I think that a lot of times we're used to. What we're going to demonstrate here is the ability to really quickly generate data, fine-tune a model, evaluate the results, rinse and repeat, go right back, find out where your gaps are, generate more data, adjust your training criteria. So what we get here is the best of both worlds. We get the fine-tuned performance of a very efficient SLM, prompt tuning, and the ability to iterate not just on our model or model parameters, but on the underlying data that's being used by the model. Next slide. So really excited to talk about this. And this is really a preview for some content and some workshops that we have coming up with Gretel. So over the past About a little bit over a year. We've been working on fine-tuning our own model, which is used by Navigator. We'll be using it today for synthetic data generation. And where we started with is a gap that we saw where any type of industry-specific format, tabular formats, things like that, in the finance industry, fraud detection formats, in the healthcare industry, like FHIR formats or things like that, that are really important. Just LLMs don't know about them. They don't know how to work with them. So in our own journey, we started with the very obvious approach of just download all of the data sets on the internet and use that to train our model. And what we see here on the left, I apologize for the small graphic, is really our journey going from working with web crawl, web scraped data to using largely synthetic data for our model training. And you see the advancements and how much faster experimentation happened as we followed this process. So there's been quite a bit in the literature about this as well, in research literature. If you look at exciting models like Microsoft's Phi-2 and their textbooks are all you need paper, for example, to even cutting edge language models like Gemini, for example, you see a real trend in the industry towards using synthetic data. Today, we're going to talk about how to do that. And in this, kind of last example before we dive into the workshop, talking about our own improvements here. So we started out with web scraping, as you see here, 500 billion tokens of tabular and machine learning data that we downloaded and worked with. The data set was large and unwieldy. And if you see on the left-hand side here, you see the number of experiments. So this is the number of model trainings and evaluations that we did per week. And you see, going from the October time period in 2023, we're hovering at about like 2 to 3 experiments per week. And why? This was a ton of data. So we needed a big, GPU cluster to rip through the data. It took us a while to evaluate the results. And then most importantly, like going from one step to another really wasn't around tuning model parameters as much as it was around tuning the data. So going through curating data, removing poorly formatted web crawled examples or things like that, searching for more examples to incorporate in there. And that really slowed down our experimentation. Starting in January, you see us adopting our own tools. So adopting the Navigator service that we built to start synthetically generating data. So tabular industry-specific formats of data. You see that the really fast ramping. And the reason we had this ramping was because now we no longer had to go back and like manually edit a data set. We could simply adjust our prompt and say, I want to generate more records like this. So as we're evaluating and we're seeing gaps in our model, we were able to iteratively improve that. So if you look at this results over a 14-day period, really, so it's over a month, but if you kind of look at it in the period there, we went from, with a much smaller model, the ability to outperform Llama 2 70 billion parameter, all the way up to the point where we were outperforming GPT 3.5 Turbo, just due to this really compressed period and rapid experimentation that was possible. So super exciting stuff. Overall takeaway here was a 35x increase in iteration speed. So we were able to test ideas so much more quickly that led to the models that we'll be using today. Next slide. So I'm going to hand it over to Martin now to start walking us through the live workshop. Martin, take it away from here.
Yeah, sure. Thanks, Alex. So we actually built a Streamlit app to illustrate an end-to-end workflow to create synthetic data sets, and I'll be sharing my screen. So give me, if the person who's sharing the screen right now can stop sharing, then I can take over. Great. There you go. So what I'm showing here is like I said, the Streamlit app for the end-to-end workflow to generate synthetic data with Gretel Navigator under the hood. And so this Streamlit app is actually built around our Gretel SDK. So I will show some code snippets within this Streamlit app, basically how we are calling things under the hood. But let's first start by initializing the application. So for that, we first need to connect to Gretel using the API key. So you go to our console page here, and in the console page, you can grab the API key and then run this and start authenticating Gretel. Once you have authenticated Gretel, a Gretel session will be created. I can actually show the code snippet here. You authenticated and initialized a Gretel session, and then we basically also initialize our Navigator model here. Just be aware that Gretel client can be pip installed, and the API key you can create, fetch it from the console. So once that is done, so once we have initialized Gretel, we select the type of financial documents for what we want to focus on and generate data sets on. So let's, in this case, I want to generate synthetic data set on financial statement, let's say also insurance policies, and maybe loan applications, right? And so what's basically happening under the hood here, I can show this code snippet here, is that we're actually going to prompt our Gretel Navigator model to generate a data set with two columns. First column is that document type we're interested in. The second is a description of a document that would align to this document type. So let's say we have 3 document types, and if we would generate 6 records in total, then it's going to generate for each document type a different description of the final document we're going to create for the synthetic data set. So let me run this here. It shouldn't take that much time. So what we end up here is a data set where we have document types and then a description of a document that would fit that document type property. And so we see that we also have one here where we have another financial report that corresponds to the document type. So going back to our demo app, the next step is now to add additional contextual tags to those. So we have now a table where we have a document type, we have a document description, but we also want to make some more contextual information to this. The language of the document, we can add the PII types that we actually want to introduce in each of those documents, and then the specific PII values. So in the Streamline app, we can set maybe up to 3 PII types in a document that we will generate, various PII values we want, and we can scale this up to a high amount of documents. In this case, I'm just going to ask the model to just generate 5, we don't want to wait too long for the generation here. And what you can see here, so we're not generating the documents yet, we're just creating those contextual tags. And now we can see that we have this, this data frame where we have a document type, document description, and then we're asking, to create documents here with a PI type, which is a phone number, social security number in the English language. And then we provide some PI values for where the model can use for, right? So pause here for a second. We have asked our Gretel Navigator model to come up with document types and a description of these documents. We added additional contextual text to that table that we generated. And now the last step is basically to call our Gretel Navigator for a second time, and as an input we will provide this table here that I just showed, where all the context is provided, and also a prompt where we basically instruct the Navigator model to and I click already here, so I start generating, to extra instructions to the model to generate the data set according to the needs we want. So in this case, we have 5 different combinations here, and I'm asking for each of those combinations to generate 3 documents. Obviously, we can scale it up as much as we want. We can also set a size length for these documents to generate. 200 is relatively small, so we can see it nicely in a table here. And so under the hood, we basically create this additional call to the Navigator model, where we prompt the model for, this is just one record in the column in that table, to integrate phone number and social security number for that particular document type fitting the insurance policy. Once I've done that, so the model has stopped running here, we can see that we have generated a document type of insurance policy. Gretel Navigator created a document text corresponding to all these tags that we provided to the model. And in this text, I can see a phone number here. I can see a social security number here. And then the second or the third column is actually a a labeling or a tagging of this PII information here that we have done in the document text. Maybe I can show another example here about loan application here. There's also a phone number here. There is a zip code here. And you can also see that this has been now labeled here. There's even an IP address that we have here. So now we have actually generated this synthetic data set with, not only just text that contains PI information, but also we have labeled and tagged the PI information in the text, and that can now be used in a to fine-tune a small or a large language model to teach the model how to identify and anonymize sensitive fields such as names and phone numbers and zip codes accordingly. So I've just generated a few records here, but just playing with all these parameters, you can make like a large scale data set of like 100,000 of records specifically to the needs and the tags you want to generate a data set for. So I'll hand it back to Alex here for the second part of the demo.
Thanks, Martin. I'll share my screen. So now we have generated the synthetic data, and our plan is to fine-tune a language model. So make sure I pick the right screen here. Apologies here. You're looking at my VS Code interface. Apologies, a lot of text and it looks small, but we're here reviewing a notebook. We will be publishing these notebooks the next day, and you'll find them accessible. We'll share a link to download this and try it yourself and customize it for your own use cases. So the next case, we've generated the synthetic data set that we can use to label or show the types of PII and the types of documents we care about. Now we want to train a model using that synthetic data that can be used in production to label any new data that I have coming with my service. We're going to be using Google's new Gemma models. These are state-of-the-art open source LLMs. They come in two different sizes currently, so 2 and 7 billion parameters. We'll be using the instruction-tuned versions, which are really kind of like set up already to deal with the types of tasks that we want to use it for anonymization. And we'll be fine-tuning it on our synthetic data set. We're going to do a pretty state-of-the-art setup here because of really the efficiency improvements that you can take advantage of. So we're going to use a few libraries. Don't have to know what they are yet. We'll walk through it. So we're going to use TRL, which is a Transformers Reinforcement Learning library from Hugging Face, and the fine-tuning trainer interface from TRL. We'll be using a technique as well called flash attention, which requires a slightly newer GPU. So you need an Ampere class GPU to do this. But it's traditional optimization techniques that result in a 2 to 3x increase in our more efficient fine-tuning for the model. So we'll see like the model fine-tuning very quickly. Last thing we'll do here is we will compare and evaluate how these models work, the 2 billion and 7 billion parameter models on our task, which is identifying PII inside of financial documents. How will they work in that real world scenario? And we can also look at where we'll iterate and where you would go for a next step with this. So with that, let's dive right in. I'm going to go through the code, but most of this is boilerplate code. Really, the only thing that you would need to change is the data set and perhaps some small tweaks to your evaluation criteria. So we'll start by installing our required libraries. We make sure that we're using a new GPU. If you are using Colab, to use flash attention, you're going to need to use the A100 GPU. You'll get really nice increased performance from there. If you're not, then just turn off the flash attention in the config when we're training. Gemma requires you to sign a developer license to access the model. So we're going to use Hugging Face Hub here. You need to get a token from Hugging Face, but then you're good to go after that. This gets into where we are loading our synthetic data. So we have a synthetic data. I dropped about 3,000 results that we generated using Gretel into GCS buckets. You can see it right here. And it's in JSON-L format. And what we need to do is to convert it into a format that Gemma knows how to work with. Gemma uses the ChatML format, which is a really increasingly becoming a standard. which is a way to fine tune and prompt models that was built, has been built out by the community over the past couple months. So here you see us taking this JSON-L data, we load it up, and then we do this create conversation. So the important parts to look at here are the system message. This is where we're telling the LM what its task is and what it needs to be good at. And then also the format that we're using. So we create a system message. You can see we also use it right here. And the system message says, you're an AI expert in entity recognition for financial documents. Users will send you text and you return only a labeled version of that exact same text without any additional context. So then we tell it what we want it to do, enclose the recognized entities in curly and square brackets like this, like we're using in the training data that Martin just showed. And then the typical boilerplate, don't tell me anything else, just give me what I'm asking for. So we do that, we load this into the chat ML format that we will then use to fine tune Gemma. So simple code here, and we'll go ahead and look at the output. So at the end here, I have it prompt out an example conversation. So this is what the input data as we're training the LM looks like. Here we have the system, we're telling it what its job is, and then we give it some examples here. So the user example is the raw data we want to anonymize. So you can see on this birthday, this project reached a key milestone, things like that. And then in the assistant, the synthetic data has the labeled version of that data. So we can see 1964, we need to label that data. So going through, now that we have converted to the chat ML format, which TRL makes really easy to do, we're going to go ahead and start the work of fine-tuning our Gemma model. So once again, we're using pretty boilerplate code for Gemma fine-tuning here, but it's got some really nice optimizations around using QLoRa for parameter efficient fine-tuning, as well as quantizing down the weights. And this allows us to tune this model very quickly. So whereas a 2 or 7 billion parameter model a year ago would have taken 12 hours to fine tune, now we can do it in just a few minutes using some of this really great work from the community. So here we're loading up the pre-trained model. You can see we've configured in this example here, we've configured the 2 billion parameter instruction tuned Gemma model. We had to make some quick changes to the tokenizer. Gemma expects a beginning and end of sentence token at the front. You don't have to worry about that. This will just work, but we're using a community tokenizer here that does that for you automatically. As we step through, we get our LoRa config and our training arguments. So the stuff to look at here is a number of training epochs. So we're doing 8 passes over the data because it's a relatively small data set. Make sure the model really has time to learn it. I think that's going to equate to about 800 or 900 steps. And then the batch size, and this is really GPU dependent. This test has been done on an A140 gig GPU. If you're using a consumer grade or like a home GPU, like with 24 gigs of RAM, like a 3090, you'll want to set this down to 1 or 2 for the batch size. But otherwise it should work just fine. And now we get right into the fun stuff. So we're actually going to do the model training. So once again, you can click through, no really special configuration here. It's just required code. We're going to train the model and we're going to save it. So here you see it ripping through on the 2 billion parameter model. We'll start to compare this versus the 7 billion. On the 2 billion parameter model, it took about 1 hour and 5 minutes to do the complete training. Let's jump over here and look at the 7 billion parameter model and see how long it took to do that. So on the 7 billion parameter model, same training took about 3 hours. So you see some efficiency gains using the 2 billion parameter model already. And what we'll do next is compare the task performance between the 2 different models. So already we can see that the 2 billion parameter model was a lot faster to train. Just took 1 hour and 5 minutes. Next, we save the model weights. We close down the model here just so we can load it up from disk and kind of demonstrate that full end-to-end process. So here we load up our new fine-tuned model that we've built. So it loads pretty quickly. Pass some example data through it. So this is just a really nice thing to do. Whenever you're fine-tuning a model, always pass in some example data, run it through, and make sure it behaves the way you think it's going to. So we pass in a few actually relatively difficult examples here. We're talking about a GPS location, which is one of the types, about 20 different types that we created for the model to learn. So we see a lat long location. Here we see US passport numbers, but we have 3 in a row. So we'll see how the model responds to that. And then last we see the address. And we don't give any zip code or state or anything like that. So once again, this is not meant to be easy, but it's not meant to be impossible either. Let's go through and look at the results. So here we can see us prompting our new fine-tuned model just on a couple examples as a sanity check. You can see it labeled it correctly. So identified this as GPS coordinates. Really nice. So we see that kind of labeled format that we're looking for kind of matched our expectations. We also see it identifying the street addresses. And then this is pretty cool, a little bit harder. Use case here where we see it successfully identifying all three of these different passport numbers. So it nailed it, did a good job. So we passed the smoke test on it. The really important thing with any model fine-tuning, any synthetic data generation is always evaluate. And so that's what we're going to dive into now is a couple different steps of how to evaluate this model, how to see how well it's doing, and then how to compare the task performance between our different SLMs that we're fine-tuning. So we step right into an evaluation step here. We'll release the code for this, but essentially we're looking at the accuracy. So how good was it at finding the PII that was inserted by the model into the data? So here we can see we're running across 500 documents. Gemma did quite well here. So this is the 2 billion parameter model trained on about 3,000 synthetic examples. We saw here that the overall accuracy was 97.28%. So it found 643 examples that have been inserted. It missed 18. That's a good sign so far. For most NER, if you look at Spacey or Flare or the popular NER packages, across typically less labels than this, the accuracy that they aim for on benchmarks is around 90%. For a highly specialized data set, you might get a 94, 95, and this really shows that some of the extra capabilities that a more powerful LLM will bring to the table. So here we see 97% detection accuracy. Let's jump over and look and see how our 7 billion parameter model did. So we'll zoom down here. And we'll go through, we load the model up, have our examples, and then we look at the accuracy here. So our 7 billion parameter model hit 98.3% accuracy. We do actually see an increase in accuracy. Where this gets really fun is actually getting in and looking at the actual results. And we have two levels. We'll look at this one. The first one I really like as an overall kind of sanity check. So this is just talking about the roughly 20 different types of finance labels that we wanted the company to recognize, or the model to recognize. How good of a job did it do? And we can see across these, we see a few gaps. Not surprising, names can be very difficult to recognize in an LM. Sometimes it looks like it's city, it's very difficult. Street addresses as well. So we see the Gemma 2 billion parameter model doing that, and also struggling. We see a little bit with IBAN numbers, it missed a little bit, US bank numbers. Let's see how the Gemma model did, the 7 billion parameter model. So going here, we actually see like kind of across the board, a little bit stronger performance, struggling in the same areas, names. It looks like it got all the street addresses, which is really impressive. And then we see a couple kind of corner cases where it looks like it missed an email address and a phone number, but overall, very, very close. For the next step, say we want to keep iterating on this, 97.3% is not good enough. Can we make it better? One of the things that we use at Gretel very heavily is this, this kind of like 2x2 comparison. So think of it as a heat map where we can look at each of the different document types we generated. For this example, we had about 10 different document types. You could also, you could generate 100 or 1,000 different types of documents. And then we look at that in context of what labels we're able to find. One that stands out right off the bat is that we see here when we're looking at IP addresses and security logs. Surprisingly, wouldn't think that'd be that hard, but the security logs may have had a surprising format for the LLM. You can see that was an area where we had a real gap. So you can see we missed all of the IP addresses in the example data for the security logs. Similar earlier, we called out names as being a kind of a difficult area. So we go ahead and look at names and say, where did it struggle here? IT support tickets was an area where it had a hard time. Also security logs once again. Security logs, not surprising because often they have JSON or XML or really kind of like very domain specific formats. So the next stage that we would do on iterating on this model is going back to our synthetic model and generating more examples, in this case of security logs with names and IP addresses, boosting that training data and going back and training Gretel again. So in that case, I would expect that we could stamp this out and probably get in the 9.8% accuracy pretty quickly. So cool stuff. Stepping on a little bit more, we also capture here, and this is one of the things that has worked out really well for us, is capture the missed detections, and you can look through it and see examples of where it failed. Here's one of the missed addresses for the 2 billion parameter models, and here we gave an address in the Japanese language. So this synthetic data set we created had a couple languages in it. One of them was Japanese, and you can see it struggled with mixed, what looks like a US and Japanese language. So we see that. Once again, we see here it also missing a let's see, this looks to be a org or company name that's in Japanese as well. So this kind of gives you an idea that I might want to boost more foreign language examples or things like that in my data. The next question is, what happens when I want to run this data at scale? I've gone through it, I've evaluated, it's getting state-of-the-art results in my data. I feel good. I've talked to my privacy team about this and they've signed off on it. What does it look like in production? And one of the questions we hear often from customers about this is like, wow, the flexibility of an SLM sounds amazing, but how do I compare that against NER models perhaps that are in before, like a BERT model, which is a kind of a an OG small language model, or more traditional NER technologies. So here we've got an example. We'll share all this if anyone wants to dive in or kind of compare it against their own notes here. One of the things that we've seen is a rapid advancement with newer LLMs. So these SLMs like Gemma, for example, are built to work fast on the types of, specifically on the compute architectures that are going out. So, a relatively powerful A100 GPU. So it's an enterprise GPU that's a couple generations old now, but widely available. We'll look at the performance here. And it's part of an optimized pipeline with Gemma. So if you're kind of stacking it up and batching, we can see about 550 tokens a second. And that's for the 7 billion parameter model. If you go down to the 2 billion parameter model, it's about 4 times more efficient. So you see here about 2,000 tokens per second. So that's pretty fast. A token, really, actually, another kind of neat thing about the Gemma model is it has a really big vocabulary. So it has about 250,000 word vocabulary. And what that means is that it can more efficiently represent most types of text. So a token is going to, whereas on a normal tokenizer, a token might equate to like 3 letters, typically 3 characters that it will map to during the tokenization process. Gemma, with a larger vocabulary and a lot of data sets, is going to get like 4. So it was quite a bit more efficient. So 4 characters per average token, which means when you're going through a document, you can get through it 33% faster, which is pretty exciting. When we look at the cost here of running this at scale, and really the last part before we start handing things over to questions here, on a 7 billion parameter model at 8.5% accuracy on an A100, here we see you can do about 7.9 million characters per hour at $1.60 per hour. That helps you kind of contextualize what the cost is going to be. So for a megabyte, struggling to see the numbers here. For 1 megabyte of text with Gemma 7 billion, that's going to cost you about 20 cents. Gemma 2 is a 2 billion parameter model, can accomplish the same task in about 5 cents. When you start thinking about running this at scale across hundreds or thousands megs of data, text data you might have, then those performance efficiency things really start to matter. So I wanted to compare this against traditional NER, which I don't think is going to give you the same flexibility or performance, but you see versus the Gemma 2 billion, about 2 to 5 times more efficient running a traditional like NER model. But you get better performance. And I think the important thing to leave with too is also kind of looking at where the industry is going. There's so much work behind LLMs and SLMs and accelerating them. I wanted to share a stat that NVIDIA just released that's kind of talking about where this is going. So today on our optimized A100, we can get about 550 tokens or 2,000 tokens per second on the 2 billion parameter Gemma model, which is really fast for an LLM. NVIDIA just announced, and this kind of shows some of the architecture improvements inside of the Gemma model, and also how it's aligned with the next generation compute architecture. NVIDIA just announced that they were able to achieve 79,000 tokens per second on a Gemma 2 billion parameter model, which almost flips this whole thing on its head. So a 40x improvement in efficiency for the Gemma 2 billion. Will cost a little bit more per hour, so estimating $8 per hour for an H200. Our cost for doing a megabyte of text can go from 5 cents to a tenth of a penny. So really exciting to see these advancements happening right now. With that, I will hand things back over. Thank you everyone for attending our workshop today. And I see we have a series of questions and happy to dive in and answer them.
Hi, thank you everyone for joining, and thank you everyone who's still on. Thank you to our panelists as well. This was a really interesting discussion. I love seeing the demos. We're going to start with Q&A here, so feel free to please continue to ask those Q&As in the chat. We had a number of questions and answers come in beforehand in the forum. We'll be getting to those as well. We have about 10 to 15 minutes here for Q&A, so we'll get to as much as we can, but for anything that's not answered, you can always kind of join our Discord community and continue the conversation there. So just to start with, these are open Q&A, as you all know. Any of our panelists can take them. So we wanted to start with a question about privacy. There's quite a number of people who are asking about anonymization of custom fields and how one can ensure accuracy of anonymization and avoid re-identification. I know we touched a little bit on it, but I think since there are so many questions, it would be helpful just kind of getting an overview.
So what we've gone through today is really, I think the most accurate term for it would be like labeling or de-identification of data. So we're taking known fields that exist inside of a data set, we're labeling them, and then we're demonstrating the ability to redact, to replace them with something else, something like that. The best way to characterize that, there is no way to answer the unknown unknowns on data you have in Dune. So the best way to do this is to create a really comprehensive test set like we did. So we allocated about 20% of the data we generated to test, and then we evaluate across that entire data set. So that'll give you a good feel for how your model is going to perform in production. At times where you need something better. So here, what we demonstrated is significantly better than state-of-the-art previous generation NER models. So here we're at like 98% detection accuracy. If you need that extra 2%, you need essentially that guarantee that the data will not be memorized or replayed by the model. That's where you want to combine that, where we're not just doing identification or de-identification of data. You want to combine it with a synthetic data technique. So how we would do this at Gretel is we use a technology called differential privacy. And we apply that during model fine-tuning time. So instead of just processing documents and anonymizing them as they go, what we would do is we would take your corpus, or you would take your corpus using Gretel. You would fine-tune your LLM on that data set. So a Gemma 2 or 7 billion parameter model, you would fine-tune on that data set. You would apply differentially private. We use a technique called DPSGD that essentially inserts noise into the data and makes sure that rare elements in the data that might have been missed will not be memorized or replayed by the model. And the neat thing here is you get a mathematical guarantee. So we give you a score, which is an epsilon or delta, that gives you essentially that confidence that what is the chance that one user in this data set could be de-identified, where you get a formal mathematical guarantee that isn't possible with other techniques. And the other really neat thing about that is you train this model, you have it generate a new corpus for you, a new data set, same size and dimensions as the one you trained on. But the really neat thing is that the other attributes in that data, for example, if you're working in the finance world and you're working with, let's say, a fraud detection data set, and you have a bunch of characteristics about each user, and some of those characteristics are PII, you would recognize it, you would remove it. Some of them aren't, like maybe your height, your zip code. Those aren't identifying by themselves, but a combination of them could become identifying, right? If you knew that somebody was of a certain height and a certain zip code and was a rare zip code, then you'd be susceptible to a membership inference attack. Differential privacy gives you formal mathematical guarantees at the cost of compute. The compute expense is a lot higher than what we just demonstrated today, but essentially you can create a synthetic data set that can be used with, within 1 to 2% of the accuracy of the real world data, with a guarantee that that would never be possible. So we'll link, last comment on that before we move on to the next question, is we'll link some research that we've published and some background on the techniques that we use as well.
Super interesting. Thank you, Alex. We have another question here, and this one's specific to Google Cloud. So I don't know, Ali, if you'd want to take this one. But a number of folks had questions about best practices. Kind of a general question, but best practices for starting using AI in Google Cloud, if you had any tips or tricks that you'd recommend folks. And there were a number of questions that specifically asked about folks that don't have as much GPU power or GPU poor startups, if you had any tips for how they could get started on GCP.
Excellent. Yeah, these are great questions. And what I would suggest is take a look at, I'm going to just try to post this link here in the chat. So this is kind of an overall reference to the Google Cloud generative AI kind of path There are various courses that you offer for free that you can take. There are various GitHub repositories and examples. Alex and Martin just demonstrated two excellent ones, very, very up to date, combining synthetic data generation with the open models from Google, which are the Gemma models, the 2 billion, 7 billion parameter models, in a very, very realistic industry-specific use cases for financial services. So I would actually suggest that you, I mean, depending on the level of sophistication that we talked about earlier, you start with, the different sets of resources that are available to you, and then ultimately try to shoot for the sophisticated example like the one Alex was showing for fine-tuning your data for your domain. And of course, there are resources there that can help you. On the GPU question or the TPU question, I mean, there's a spectrum of answers. These are things that are very, very much in high demand across the industry. Google provides Google Colab, that you can leverage to get started. But if you want to do intense pre-training, of course, you would need much more compute. And therefore, you could go to the console in Google Cloud. And there are various types of offerings that we have for TPUs and GPUs. They can do fine-tuning, full fine-tuning, or parameter-efficient fine-tuning that will require much less initial data, much less compute. So there's a spectrum of solutions that you can have, starting from very lightweight to very heavyweight, intense with the data, intense with the compute. And so you can pick across that spectrum. One of the points that Alex was making, that you start out with your data that can be synthetically generated, like Gretel, and you can then start experimenting on how well your taxonomies and ontologies in your domain respond to models that are tuned in this fashion. And then you can decide to go to more and more sophisticated, higher levels of data and compute as needed. I hope that answered your question broadly.
That was great. Thank you, Ellie. And for anyone who needs that link, that's in the chat. So feel free to dig in there. There's another question here. This question was submitted live. I think it's an interesting question about synthetic data and our synthetic data model in general. The question is, if any of the panelists want to see, you could click the Q&A little button at the bottom. It's a bit of a long question, but I'll kind of read it out loud. Folks are asking about how robust the synthetic data model is in case of misspellings. And considering real-life financial data might come from both typed or online filled documents and handwritten documents scanned using OCR software. And there's a second part to that question as well, asking that given the model's generation of synthetic data, is there a possibility that this data is very clean, thus contributing to very high accuracy? How does the model ensure diversity and realism of the data to mimic real-world inaccuracies?
Good question. Martin, you want to start on that?
Sure, yeah. So yeah, with respect to having misspelling, spelling errors, and possibly another source, like maybe it's transcribed audio, right? And maybe there's some ASR transcription errors in the data. You could also ask the Navigator model to be aware of the source of the data, and it can introduce some spelling errors as well if that is something you want to achieve in your synthetic data to make the downstream application more robust. So that's definitely one way to do that. So force introduction of those imperfections in the data. While it's contributing to higher accuracy in the entity, I'm not sure about that, Alex. I think the most accuracy boost came from fine-tuning on PI detection labels, and not because the data has been very clean compared to the source data.
Yeah, we found as a pattern when you're training models, One of the areas that we've really been able to help kind of increase accuracy is by taking your training data. That maybe an easy way to think of it when you're passing it in isn't always like super high quality. Like you would have a user talking on a chat transcript to a support person. It's training on that. We just sometimes ask the synthetic model to create, instead of like giving a question and an answer, to ask the question in an iterative, like multi-step way and kind of answer it like a teacher would answer a student. So essentially, it's called like step-by-step reasoning, but just kind of walking through how to arrive at that process. And that can help quite a bit with improving accuracy for LLMs as they're being trained.
Okay,
I thought it was a
great.
really interesting question. It's a side topic too about the how do you maintain some of the like the dirtiness in the original data. We've heard that come up. There was a HL7 conference, medical conference, and one of the biggest problems they've been working with a data set, a statistically created data set from MITRE called Cynthia, which creates synthetic patient medical records. And they called out the biggest pain point they had was the data was too perfect and didn't allow them to stress test their systems. So this is a case where providing a prompt or providing some examples, you can have this model really kind of introduce some variations that will surprise your models if you're using it for like a testing type use case.
Cool. And we're about to hit the 1 hour mark in about 3 minutes. So I think we'll just take one final question. Before we do that, I just wanted to give a shout out to both Google and Gretel. With Google Next coming up next week, I know we're really excited about a number of things there. I'm sure everyone on this call is excited as well. Gretel will be there as well at booth 1735. I've included a link in the chat for anyone who's interested in exploring Google and Gretel together can fill out kind of your information there. So feel free to reach out there. And we'll end, I don't know if anyone else wants to add anything, but we'll end with, feel free to after I ask this question, but we'll end with this one question. We had someone asking about showing an example by generating some random data or just data through Gretel. I'm not sure if you might want to showcase one of our interfaces where you could kind of viscerally see kind of prompts and results in real time.
Sure, I'd be happy to. Murtaza, let me share my screen. Can you enable me for screen sharing? Thanks.
Yes.
So I will just jump into the Gretel console. You can follow along for free if you would like. So we have a free tier. And I just need to find my window here. 1 second. So here I've logged into the Gretel console. Hopefully you guys can see this. And I'll click on Model Playground. And this allows me to interact directly with our Navigator, so our tabular LLM generation tool. I could do something as simple as just random data set that I wanted to generate here. I'm sure we've all done this at some point. Create a mock data that I could use for my an application. So here you see it generating a large quantity of mock data that's useful. Another one just for kind of a fun example, I like this one quite a bit. So what we can do is a very kind of typical use case is that I want to extract question context truth pairs from a document. So I'm going to go ahead and delete this. I'm going to search for Google Gemma press release. Let's take a look. This looks neat. I'm going to grab all the text from this document, including all of the extra junk in there, HTML tags and things like that. I'm going to pass this into my model and to say, just generate question, truth, context pairs. So you see an agent-based architecture here running. So essentially it's taking your question, dividing it into little pieces that it can execute on. It's extracting the context from the text and then giving you a high quality question and truth pair. So those are some examples. If you want to take it a step further, just go to docs.gretel.ai. From there, click Gretel models and Navigator. And we've got a bunch of examples here. I would start with this Colab, which is the high-level SDK interface, just to show you how simple it is really to generate data with Gretel. Here we go through generating both synthetic data and then editing a data set itself, just in a few lines of code.
Cool. Thank you so much, Alex. I don't know if you want to give any ending thoughts or.
No, thank you to everyone for exciting. So I definitely appreciate everyone joining here today. Ali, always great working together, and really excited for next coming up. So I'm sure there'll be lots of excitement around that, and looking forward to next steps.
Yep. See you there. And thank you very much for the invite.
Cool. Thanks, guys.